Oh, hello everyone, and welcome to another audio podcast series. This is the Shientist, and this series is part of the Shientist Charter Edition, and the general episode for this series is the Busta Cap episode, and it's part of the Storm Lobostics production, and the the Shientist Chartered Edition will focus on several topics surrounding immunology, hematology, and transfusion practices. The storm this this again this particular Storm Robotics production audio podcast series will introduce the following subject entities. So I'll be talking about the definition of blood and haemopoiesis, the use of red blood cells, the use of platelets and granulocytes, the use of human albumin solution or has, the use ABO blood group systems, the immune the immune hemolytic anemias, and then finally antibody screening and identification. And part of this, I am going to have made available through the Storm Robotics Instagram channel, and there will be um, uh, a series of presentations around this on the Storm Robotics Research and Education Center through YouTube, through the YouTube channel, at least one of the YouTube channels. Basically, I'm going to start off by talking about what the blood and haemopoiesis as part of the Busta Cap episode. So to begin with, some basic definitions, and then we I'll talk a little bit more about some other aspects around haemopoiesis. So some definitions to begin with. So haemopoiesis, or haematopoiesis, is the production of red blood cells or blood cells which in normal healthy adults occurs in the bone marrow and the lymphatic system. During fetal life, haemopoietic tissue is found in the liver, and spleen. And an underlying aspect here is the liver is important in relating to the development, and kind of the harboring of what is known as the clotting factors. And the clotting factors won't be discussed in this particular presentation, but generally speaking, the clotting factors are part of what is known as intrinsic and extrinsic pathways, and a common pathway, which is where both intrinsic and extrinsic clotting pathways sort of meet. And then the spleen is obvious is important in part of hematology, at least in relating to antibodies being sort of housed in a way, if you like, as part of general physiology. Now, because all blood cells have a limited lifespan, ongoing replacement of cells that are no longer viable is needed. This happens by division and maturation of what are known as precursor cells, mainly in the bone marrow. Self-renewing stem cells can develop into either of the two types of cells, one giving rise to red cells, or what are known as also known as in hematological in what are known as from a hematological standpoint erythrocytes, and platelets. And platelets are those cells that are important for blood clotting. And the other giving rise to lymphocytes and natural killer cells. Lymphocytes are related to in hematology. Lymphocytes are white blood cells, and natural killer cells are also part of white cells as well. Abbreviated in publications, NK cells are normally referred to as NK cells. Mature cells are released into the bloodstream, where they circulate and continue to age until they are no longer functional, at which time they are withdrawn from the bloodstream, broken down, and the elements either reused or excreted. The specific blood cells that are produced and eventually released into the bloodstream are the red cells or erythrocytes, the various types of white cells or leukocytes or lymphocytes, and the platelets or thrombocytes as well. All these are formed elements or cells all of these are formed elements and originate commonly or even ancestrally from stem cells that are after many cell divisions in the bone marrow have sort of taken place and result in the mature cells that are found actually in circulation, i.e. In this context is the definition of haemopoiesis or haematopoiesis. The precursor cells are also known or can be referred to as blast cells. Example: the precursor lymphocyte is called a lymphoblast. A normal peripheral blood contains what are known as mature cells that do not undergo further division, and mature erythrocytes and platelets are also referred to as non-nucleated. Erythropoiesis is another form of red cell production, where basically red cells are stimulated through the hormone erythropoietin, which is commonly produced by the kidneys. And red cells contain hemoglobin, which is needed. Red cells contain hemoglobin, which is needed for the transportation of oxygen in the bloodstream to all parts of the body. And throughout fetal life, something that is referred to as fetal hemoglobin F or HbF is produced by maturing red cells, and it's only after birth that adults have that adult hemoglobin A or HbA predominates. So a bit more around around some definitions, and there's 5 main things I'm going to talk about here. Number 1 is around linking with haemopoiesis. There's hemostasis. So hemostasis is a terminology that is used to describe the control of bleeding, the formation of a clot or a blood clot, and in the time of healing, the resolution of the clot, of the blood clot and a return to normal. So when someone bleeds and a blood clot forms over, let's say for example, over a particular wound, from that time that the clot is forming, a blood clot is forming, then until there is normalization around a particular wound. For example, that can be referred as what is known as hemostasis. And generally, the process has four major components, however. Um, so there's something that is known as vasoconstriction, and vasoconstriction is where vascular constriction occurs in damaged in a damaged blood vessel, for example, with a muscular wall. So this means that the blood vessel contracts or tightens to minimize further loss of blood. Then there is something known as the platelet plug. The platelet plug is basically where blood does not clot in the body because blood does not clot in the body because there is insufficient free thromboplastin. Thromboplastin is part of the is part of the elements that make up that cause the clot to form. So for clots to form, calcium is needed. For example, calcium is needed, and also part of the factors part of the factors in relating to the intrinsic and extrinsic pathways, and also part of the common pathway is where thromboplastin also originates to actually form a clot successfully. But blood clots blood does not clot in the body if there is insufficient free thromboplastin. However, as a result of injury, thromboplastin is naturally released, and in the presence of calcium ions, and combines with what is known as prothrombin to form thrombin, and which then in turn activates platelets. So overall, a platelet is formed, and then activated platelets amplify the response by activating more platelets and something that is known as fibrinogen, which stimulates the sticking together as a soft plug. So when you see when you actually see a blood clot, it looks basically where it's sort of stringy, but also like something that's plugged up, and that's plugged. So activated platelets amplify the response by activating more platelets, and fibrinogen stimulates the stickiness, which is then together with the fibrinogen and the prothrombin and to form thrombin, is then where the stickiness brings together a soft plug that loosely blocks the wound, and also dramatically slowing down the bleeding, where bleeding is taking place. Now, clot formation is also important around this. Clot formation specifically is where each clotting factor has, in the meanwhile, been always participating in the process, which is why it is called a coagulation a coagulation cascade. So where I've mentioned, for example, there's the intrinsic and extrinsic and the common pathway. Those are what are referred to as the coagulation cascade, or some hematologists refer to this as the clotting cascade. And so a mesh of insoluble fibrin is finally then formed, resulting in a platelet plug, and so reaching an endpoint of clot formation. And as the clot shrinks, a clear fluid or serum is excluded. So when you think about when a clot has formed and formed altogether as part of clot formation, what happens is there can be some fluid some fluid that is almost basically what looks like pus, but that is actually where the clot, where successful clotting has formed, or clot formation has taken place. Also means that the pus is part of the clear, or a part of where the clot has where clotting shrinks, where clot shrinks, and basically a clear fluid or serum is sort of extradited from the wound, from the wounded area. Then finally there is what is known as the dissolving the clot. The last component of hemostasis is where there is a component of the component around this process is carried out by the enzyme plasmin, which is responsible for the gradual absorption of the clot by the body. So thus then to return to normal is eventually achieved. So in the next slide, or in this slide, I'm just going to give sort of a highlight of what it looks, what a blood vessel looks like inside. So this is an illustration, and I'll give the reference for this at the end of this presentation, or this slide set. So basically within a blood vessel you have your red cells, you have your platelets, you have plasma, and you have white blood cells. Generally speaking, blood cells are made up of liquid and cells and cell pieces, for the lack of a better terminology. And if patients lose some of these sort of ingredients, they may or will require replacing. In this context, I'm now going to talk a little bit about anemia. Generally, anemia is typically, in a sort of broad brush perspective, is where hemoglobin levels have drop owing to particular incidences. For example, a typical example can be hemoglobin can drop if someone if people, for example, have an accident, have an accident and lose blood, etc., etc. Now, anemia is a word generally used to describe, in broad terms or terminology, a state of red cell deficiency, either in quantity or quality. And actually, both quantity and quality have to be in balance, in where anemia, to offset anemia. An erythropoietic stimulus or trigger is needed for the body or physiology to initiate the production of new red cells, to maintain the balance between red cell production and also red cell loss. Erythropoiesis is dramatically increased also when there is a sudden substantial loss of blood. However, a very gradual yet regular or consistent loss of red cells over a long duration or a long time may actually not result in adequate compensation, and an individual could gradually become anemic without obvious signs or symptoms until the hemoglobin level is actually dangerously low. So in this context, then, the major factor controlling the rate of red cell production is actually oxygen content of the blood. And when I talk about oxygen content, what I mean is, again, referring back to where hemoglobin, is where, generally speaking, again, there has to be quantity and there has to be quality, because generally, the red cells are sensitive to actually losing oxygen quite quickly, and it's a mechanism that is actually quite clever, because basically, automatically, the body, or from a physiological standpoint, reacts. A low blood oxygen level leads to low tissue oxygen, and it's a condition that is actually referred to as hypoxia. And hypoxia is actually perhaps one of the strongest stimulus for erythropoiesis, as seen in the compensated erythropoiesis occurring in individuals living at high altitudes. So those who are at high altitudes may have, for example, higher hemoglobin levels. And there is a condition, from a hematological standpoint, there is a condition where the hemoglobin in individuals who are at higher altitudes versus the general population, for example, from a hematological standpoint, there is a terminology, and that is something known as, where red cells, where the hemoglobin level under microscopic examination, there will be more red cells, because of, at higher altitudes there is there can be less oxygen, and thus there's compensation in relating to red cell production. So what happens, the terminology is something that's referred to as, where the red cells are referred to, or the condition that is referred to as polycythemia. And so, in this regard, there is less oxygen in the air at higher altitudes. So inhabitants in such areas actually require more red cells to attach sufficient oxygen than individuals living, let's say, for example, at sea level, where oxygen in the air is greater supply. So at sea level, because of water being around, there is generally more oxygen availability in that sort of atmosphere. But at high altitudes, there's a different sort of scenario. Hypoxia does not have direct control on the bone marrow, but causes the release of a hormone, as mentioned, called erythropoietin, produced in the kidneys, which then stimulates the bone marrow, causing erythrocyte forming cells to differentiate and divide, and eventually form red cells, or erythrocytes. Erythropoietin also causes the release of cell types called reticulocytes, which are actually immature red cells. Now, reticulocytes, by the way, are also, for example, if the hemoglobin drops, let's say, for example, the hemoglobin is abnormally low, then what happens is, from a hematological or laboratory practice standpoint, the scientists, what they would do is actually prompt the initiation of a blood film to be done to actually add on blood film to be done, but also to add on the observation, or add on the analysis, of reticulocytes, to actually understand whether the red cells that are part of the hemoglobin in individuals with a low hemoglobin count, for example, whether those red cells are breaking down too fast, or whether there is an underlying morphological issue around the patient's red cells. So reticulocytes, or retics, in an abbreviated way, are actually very useful to look at, and these are generally immature red cells, and they can be part of the circulation in early life, but also in where there is, for example, there's more red cell production, red cell breakdown, when generally speaking, where, for example, in a like for like scenario, under microscopy, someone else's red cells could be completely normal, versus someone with a hemoglobin of, where hemoglobin is being compared, let's say. Now, the increased red cell mass then increases the amount of hemoglobin available to deliver oxygen, so that the tissue oxygen level is increased. The sudden loss of moderate number of red cells through an accident, for example, or by donating a unit of blood, for example, is sufficient to actually stimulate the production of red cells to replace that loss. Now, I want to make a particular emphasis on this particular note, because when you think about it, when someone's red cells have, let's say, depleted them, it's quite amazing that automatically, like, say, for example, where for example, without the body even having to sort of think, where the brain or the central nervous system without the central nervous system being sort of fully aware in that time, automatically, physiologically, what happens is that the bone marrow, along with the bone marrow, and along with what is known as I mentioned, the hormone erythropoietin, actually senses the loss in red cells. And actually, when that happens, suddenly, for example, where red cells have been depleted, at that point, the where red at that point, the sudden loss of where there's a moderate number of red cells through an accident, by donating a unit of blood, for example, for someone who might need blood, for example, that can actually stimulate the red cells via the bone marrow, and also through the hormone erythropoietin, as mentioned, to actually not just stimulate, but also get stimulated by the replenishment of red cells, but also actually can bring the hemoglobin level back to a normal sort of within the normal reference range. So here I've talked a little bit about anemia. I'm now going to talk a little bit about some the different types of blood components. And there's 5 main type ones here. And I'm just gonna go through this quite quickly, actually. So there's the red cells, or the red blood cells, which are the living product that contains in the main contains hemoglobin. Hemoglobin allows oxygen to be transported within the cell to the tissues. And then you have platelets, which are made of cell fragments, and they help blood clotting processes. And then there's plasma, which is also known as, so in common everyday language, for example, plasma is generally referred to as plasma. But from a hematological standpoint, if for example someone loses a lot of blood or hemorrhages, for example, then scientists can actually with physicians can see if what is known as fresh frozen plasma, or FFP, which could be part of a requirement to help replenish clotting factors, antibodies, enzymes, electrolytes, even hormones, and nutrients, and even certain particular waste products, because even with FFP, generally in circulation, there's whole blood and there's plasma. Whole blood is considered obviously the main source of where hemoglobin is around. Plasma is basically considered as generally as a liquid or a fluid that carries or transports different types of components, as mentioned: clotting factors, antibodies, enzymes, electrolytes, hormones, and nutrients. And generally, where all of the plasma generally is concerned, it is generally concerned as a waste product in some context. Then there is actually something called cryoprecipitate. Now, cryoprecipitate is where you have clotting factors, fibrinogen, and something that is known as factor 8. And cryoprecipitate, its main use is a source is in the source is a source of what is known as fibrinogen. And then you have finally as part of components or blood components, you have white blood cells. Now, these cells generally destroy infections, but only work well when they are when they are obviously within the body and within physiology, and so they are often removed from blood donations through blood filters. So if anyone is thinking of donating blood or has been to donating a blood donation site, for example, generally speaking, attached to a unit of blood is a filter. And what happens in that filter is that blood that is components or white cells that are being removed from that from whole blood, so that if someone is being transfused, the white cells or leukocytes or lymphocytes or even another types of white cells, white blood cells, for example, won't attack and cause a potential reaction to someone who might need need the blood component. Then I'm going to just talk a little bit about the sort of the general sort of appearance of red blood cells. So red in this slide is a general illustration of what a red blood cell looks like, and generally red cells are living cells about 7 to 8 micrometers in diameter. They have a flexible or concave type shape, and they generally, as mentioned, they contain red hemoglobin, and they are unique. They have a unique shape and inner components that allow them to efficiently transport oxygen and direct the elimination of carbon dioxide. So when you think of when you're taking in oxygen, carbon dioxide is being released, and when breathing out is when carbon dioxide is also being processed to actually form effective oxygen. The general sort of movement in relating to this process is, if you think about taking in oxygen, your diaphragm from your lungs. So taking in oxygen, the movement of your lungs are in and up, and when you are breathing out and releasing carbon dioxide, is where your lungs are going are deflating or going down, and then you're breathing out. So it's in and up, down and out. Now, when you have that process as part of let's say, for example, as part of a mindset, even then, or in one way, then it actually is a reminder of what red blood cells do, what their function is. And so I'm now going to talk a little bit about something called a red cell coatings. Now, this delves into the different types of blood groups, and so generally you have Group A, Group B, Group AB, and you have Group O. And so on each of these different groups, you have blood groups, you have different antibodies that are present, and you have different antigens that are present. So I'm just going to go through this, and what it is in red blood cell type group A, those who are blood group A, the antibodies that are present are anti-B, and the antigens that are present is antigen A. On group B, those who are blood group B, the antibodies that are present are anti-A, and then the antigens that are present are B antigen. And in group those who are blood group AB, who have components that link to both blood group A and blood group B, the antibodies that are present actually are none. They don't have any antibodies, and in antigens, the antigens that are present are actually both anti-B, are antigen A and antigen B. On group O, those who are blood group O, they have the antibodies that are present are anti-A and anti-B, and then those who the antigens that are present are actually none in those who are group O. So all humans have what are known as chromosomes, which hold the DNA and chromosome and something that is referred to as chromosome 9, which is has a gene that makes the ABO blood enzyme as a particular blood enzyme, and it's termed as N-acetyl galactosyl transferase, and this is the enzyme that actually makes the A blood group antigen. If you have a small mutation in this particular gene, you either make a different enzyme that makes B, or you don't have the enzyme at all. So generally, if you don't have the enzyme at all, then you are generally from a blood grouping perspective, group O, where you do not where an individual will not have any antigens present. So some people have both versions of the gene and make group A and group B make antigen A and anti-A, anti-B and anti-B. All red cell coatings, all red cells have coatings and generally there are four main groups, as mentioned, and so groups O and A are actually more common than B and A than B or AB. So generally these this slide in this talking about when I'm talking about red cell coatings, the main points on here to know are around how O and A again are more common than B or AB. So I'm going to talk a little bit about the compatibility aspects around blood, and generally in this slide, I'm just going to talk a little bit about how which blood group can which blood group or donation from donations can actually help in situations where where individuals might be group A, group B, group A or B, group A, group B, and group A, B, and O, and which blood groups they can actually have blood donations from. So from group A, you can actually have receive blood from O and A. From B, if you're group B, then you can have you can receive blood. You can have blood from those who are O and B. If you are A and B, AB, sorry, group AB, you can have have blood from all groups, generally speaking. If you are O, then you can only have those who are from blood group O. And in this slide, also, so I'm going to work a little bit backwards on this slide. So I've talked about what the blood groups that relate to the blood group and how if blood is needed, then which blood groups can be, which individuals which donations from blood donations, for example, can be donated to those particular blood groups. But then in this slide also, in this slide set also, this particular slide also, I'm going to talk about how those from blood, the different blood groups, who they can give blood to. So if you're from group A, blood group A, you can give blood to those who are group A and AB. So notice how it's different. So if it's something that's needed, if someone is from group A and they need blood from let's say in a scenario, then basically they can only have they can only really have blood from those who are O and A, but they can only give blood to those who are A and AB. And if you're group B, you can only give blood to those who are B and AB. If you are AB, group AB, then you can give blood actually to those who are AB and all groups. Generally, all groups. All groups can donate to those who are AB. If you are O, then you can give blood to all groups as well. And you can only receive, as mentioned before, you can only receive blood from those who are O. The other parts of this, parts of this slide talk about antigen and antibodies, and I'm not going to go into that again because I talked about that in the previous slide. So generally, blood. So group O can be safely given, and this is a sort of a main point here I want to make, that group O can be safely given to all groups of patients in life-threatening life-threatening situation or scenario, as there are no no A or B antigens to react with the recipient's antibodies. So donations from blood group O, for example, can actually be used in emergency situations, and generally where, for example, there may be a shortage around different blood groups, for example, where blood groups and stock levels around blood haven't actually been around in hospitals, for example. Now I'm going to talk about a few other components. I talked a little bit about these before, but I'm just going to make a little bit of an emphasis here. So the other blood components are platelets and also fresh frozen plasma or and or cryoprecipitate. And basically these are stored. So platelets are stored in a laboratory at 22 degrees centigrade. At 20 stored in sort of at room temperature, and normally sort of left on what are known as agitators before actually where a patient or individual might need them, but must be given promptly as and when a request comes through them, because after a certain duration, actually platelets are next to useless. Then there's, as I mentioned, plasma or fresh frozen plasma and or cryoprecipitate. And what happens is FFP, fresh frozen plasma, must also be given promptly. Must be given promptly if not stored at fridge temperatures, and cryoprecipitate must be thawed out and must be given promptly as well, much like platelets. Platelets again must never actually be put in a fridge, and generally, because fresh frozen plasma, cryoprecipitate, and platelets actually look similar when they're bagged up. It's not unheard of that issues have happened in hematology and transfusion labs where there's been a mixture, at least in relating to for example, where one has been, for example, there's been mistakes in relating to the storage of these particular blood components. So now I just want to talk about a little bit about a little bit of emphasis around the storing and the giving of these different blood components. So red blood cells, you have the storage for red blood cells is between 2 and 6 cold temperature or cool fridge temperature roughly, and the time out of the lab before infusion. So between the time a request for from a physician or someone in treating individuals or patients, the time out of the lab before red cells or red blood cells are used is really maximum 30 minutes. And the total time for infusion should be around 10 minutes, and 10 minutes in what is known as a major hemorrhage, and otherwise up to 4 hours. So generally, the red cells in where, let's say, for example, someone has a form of a particular hematological condition, and their life relies on having blood donations, or their life relies on having sort of particular red blood cells, then generally they can be infused up to 4 hours. So it goes into the bloodstream or into the blood stores within general physiology at a slow and steady way. In a major hemorrhage, of course, the time for infusion is increased maximally, because in that time, basically, individuals can have wounds where they're bleeding out and they're hemorrhaging, and there can be incidences where the bleeding or the wound, for example, is completely foreign. Like people, like in surgery, for example, people have found to have been in incidences where there's been incidences to know that people actually don't know where the bleeding is stemming from. So basically, it's important to replenish the blood cells that have lost in the first place. So then it's actually a way to find out where the bleeding actually has started from. And then for red cells, there's a shelf life. So it's 35 days, but 14 days if the red cells are irradiated. And I'll talk a bit about the different definitions around the types of red cells, irradiated and non-irradiated, in another presentation at some point. And general comments around this is that the red cells or red blood cells are only stored in designated. They can only be stored and should only be stored in designated blood fridges. Then there's the platelets, and the platelets are perhaps one of the most intriguing sort of blood components. So they have to be stored at room temperature, but also left on an agitator, as mentioned, and basically if there's a request for platelets to be used, then generally it means that they have to be collected and immediately used. If, for example, they are collected and not used, then generally speaking, those in transfusion or hematology laboratories can ask for that to be returned ASAP, so that someone else may find it useful if needed. The total time for infusion around platelets is anything from 30 to 60 minutes, and the shelf life for platelets is around 5 days. Generally, one of the main comments is that these platelets should never be stored in a fridge that causes them to aggregate and become non-functional, because as mentioned, platelets are important for clotting, and where clotting is concerned, as mentioned, I talked a little bit about how clots are formed, and basically platelets are very sensitive to clot formation, even at room temperature, if not left on an agitator. And then there's a fresh frozen plasma, which actually looks a bit like platelets, but these are actually where these blood components are frozen. They're actually put in a freezer or in a freezer type condition, and it takes about 40 minutes to defrost. And generally there's general hematological practice informs that these should be infused or used if used 12 mils per minute, or 20 minutes for 250 mils. So fresh frozen plasma, generally speaking, individuals or requests or individuals don't really have unlike for example red blood cells, there's not a massive request for fresh frozen plasma. However, that being said, the sort of shelf life for these is also that once they're thawed out, so once at room temperature, after, let's say, for 4 hours, thawed out after 4 hours, because again, these are blood components that are frozen, so it takes a number of hours to get them to room temperature, and so once thawed out, they can be left at room temperature for around 24 hours. But safe practice would be that they should go in a fridge at fridge temperature, in the same way that that red blood cells would be. So for general safe practice. And then fresh frozen plasma is stored below 30 for up to 2 years, and can take up to 40 minutes to defrost. Cryoprecipitate, and this is the final component I'm going to talk about, at least in this slide set. Cryoprecipitate is like fresh frozen plasma. Cryoprecipitate has to be stored at the same freezing temperature. So at anything at the same temperature again as fresh frozen plasma, and can also take 40 minutes. Can take up to 40 minutes to thaw out or defrost, and the total time for infusion, if there was a request for someone who needs cryoprecipitate, for example, it can be anything from should be around 12 milliliters per minute, so 12 mils per minute. And once thawed out, it can be left at room temperature for a maximum of for 4 hours at room temperature. So in some way, cryoprecipitate has a little bit more in relating to fresh frozen plasma. Cryoprecipitate is in some way more sensitive in relating to its shelf life, and it is stored at frozen temperature, so below 30, for up to 2 years, and can take up to 40 minutes to actually defrost. Now I just want to say thank you for taking the time to listen to this presentation on definition of blood and haemopoiesis. This has been an overview on what the blood and haemopoiesis, and just some general references and acknowledgements. In relating to the literature, I've referred to a particular book publication, the International Society of Blood Transfusion, and it's the Science series from 2020, and it was a special issue, and it's an introduction to blood transfusion from donor to recipient, and it's actually available or through the International Society of Blood Transfusion, and part of their science series. And I also want to say I want to acknowledge two senior or renowned scientists that have focused their work around immunology and transfusion. So, firstly, Malcolm Needs, who is a transfusion scientist and practitioner from the United Kingdom, for his approach to hematology and transfusion, and also to a Professor Ken Jones, who is an emeritus professor in immunology, also based in the United Kingdom, for his perspective around the immunological aspects around this work. So thank you for listening, and this has been the first presentation in the Busta Cap episode as part of the Shientist and the Shientist, and it's been another Storm Robotics production. Thank you for listening, and hopefully I look forward to doing the next one on the use of red blood cells. Thank you.